Hi everyone, today we're going to learn how to graph log and exponential functions. Before learning how to graph them, we want to explore a little bit about each of these graphs. We want to find the domain, range, x and y intercept, end behaviors and asymptotes of each of these functions that you see here. I'm going to use Desmos to get help find this information about this function. So the first function is y equal to 2 to the power of x. And I want to find the domain and range of this function. As I look at the graph of the 2 to the power of x, we see that to find the domain of this function, I need to move from left to the right. And as I move from left to right, there is no restriction here. So the domain of this function is all real numbers, or from negative infinity to infinity. To find the range of this function, I need to move from bottom to top. So as I move from bottom, I see that there is no part of the function defined for negative y values. So no negative value is defined for the range. The range of the function starts from 0 and goes to infinity. And as you see, we have an asymptote here at y equal to 0. At y equals 0, my function is getting close to 0 but doesn't pass. That means there is an asymptote at this point. So this is the domain and this one is the range of the function, and the asymptote is y equal to 0. Let's look at the x and y intercept of the function. If you look at this function, you see that the function is not passing through the x-axis, so there is no x-intercept, but it's passing through the y-axis, and that's at point 0 and 1. This is the y-intercept of the function, so this is the y-intercept, 0 and 1. Then we need to look at the end behaviors, right end behavior and left end behavior of this function. At the right end behavior of the function, like this part of the function, I see that the function is continuing forever. It's going up and up, it's increasing. So I can say as x goes to infinity, my y is going to infinity. On the left side of the function, the left end behavior, x goes to negative infinity, but the y is getting close to 0. So this will be the left end behavior of this function. If you check the function of e to the x and 10 to the x here, we will see that the general form of the function of e to x and also 10 to the x are the same. For all these three functions, the domain is from negative infinity to infinity, range is 0 to infinity, and then the x-intercept does not exist. Y-intercept is at 0 and 1, and also the right end behavior is infinity, left end behavior is 0, because we have an asymptote at y equal to 0. So all these pieces of information are the same for 2 to the x, e to x, and 10 to x. The only thing that I want you all to pay attention is the point 0 and 1, and 1 and the base that you see here I have written for all these functions. For example, for 2 to the x, I have written 0 and 1 and 1 and 2. What are these 2 points? 0 and 1, as we just talked about, is the x-intercept of, the y-intercept of the function. But 1 and 2 is a point which is kind of, we can say, constant point that always exists on all these kind of exponential functions. We always have 1 and the base for all the exponential functions on the graph of this kind of function. So for 2 to the power of x, 1 and 2 always exist. For e to the power of x, we have 1 and e at this point. 1 and e is a point that exists because the base is e. And for 10 to the power of x, we have 1 and 10. So 1 and the base always exist. These 2 points are we can say the most important points of the graphs, which always exist, and we can use them to graph our function. We'll talk more about these later. Now let's go to the next table. In this table we are going to find this information about log functions with different bases, base 2, base e, and base 10. So here we have log base 2, and as you look at the function, the domain, as I move from left to right, is starting from 0. I have an asymptote at x equal to 0. The vertical asymptote is x equal to 0, and the domain starts from after this point. So from 0 to infinity is the domain of the function. And the range, as I move from bottom to top, I see that it's from negative infinity to infinity. So this is domain and range of the function. The x-intercept is this point where your function is crossing the x-axis. But the y-intercept does not exist here. The right-hand behavior of the function is as x goes to infinity, y is also going to infinity, because as you see, it's always increasing and going to infinity. The left-hand side of the end behavior of the function is when x goes to the 0, not infinity this time, because the function is getting close to 0 and doesn't pass this point. So as x goes to 0, y is always decreasing and going to negative infinity. So we need to make a small change here. The left end behavior is that x goes to 0, f of x goes to negative infinity. So all this information are the same for natural log and log base 10. They are going to be repeated for all of them. Also, I need you all pay attention again to the two important points of this function. For log base 2, 1 and 0 is the x-intercept. Another point is the base and 1. The base is 2. So 2 and 1 is one of the constant points that always exists on this function. If you consider natural log function, again the same thing. 1 and 0 is the x-intercept, and e and 1 is the other important point on the graph of this function. Log base 10 also has the same situation, has 1 and 0 as the x-intercept and 10 and 1. So these points are the important points of the log function. We will talk more about these in the next part of the lesson. So let's just compare the two functions of 2 to the power of x and natural log of x. So 2 to the power of x has this shape, and natural log is kind of this shape. If you look at these two functions, you will see that let me just draw them on one same coordinate plane. So natural log or log base 2 looks something like this, and 2 to the power of x looks something like this. As you notice, these two functions are reflected over y equal to x. That means these two functions are inverse of each other. So we can always say exponential and log functions are inverse of each other. So here, if you graph e to the x and then y equal to natural log of x on the same window, we will see that they are reflected over y equal to x, and that means they are inverse of each other. So in this example here, we want to learn how to graph an exponential function with any base. So Base is not a special number, specific number here. It's just a value a. I want to learn how to graph this function. We always know that in order to graph a function, we need some points. So here we're going to use the same two important points that I just talked about. How do I get those 2 points? In order to get those points, I'm going to set x equal to 0 for the first time. So if x is 0, y will be a to the power of 0, which is 1. So 0 and 1 is one of the points. For the other one, I'm going to set x equal to 1. So y will be a to the power of 1, which is a. So as you see, now these are the two important points that we talked about. 0 and 1 and the base are the two important points. So I can find them on my coordinate plane, 0 and 1 and let's say a is here. So the point will be here at this point. We also learned that exponential functions have an asymptote of y equal to 0. So we have a horizontal asymptote here at y equal to 0. Now we can graph the function. Just connect these 2 points and get close to the asymptote, like this. Because we already know the graph of exponential looks something like this. That's why as we just get these 2 points and the asymptote, we can easily graph the function. So the domain of this function, as we learned before, is negative infinity to infinity. And the range from bottom to top is 0 to infinity. Now let's see how we can graph log function. Again, for log functions, we need those two important points. How do I get the important points of log? So for the first time, I'm going to set x equal to 1. So what would my y value be? The y value will be log of 1 base b. And we know that log of 1 is always equal to 0. So it's 1 and 0. The next point, I'm going to set the base as the x value. So it will be y equal to log of b base b, which is 1. So the 2 points are 1 and 0 and b and 1. So I can graph these 2 points, 1 and 0 and b and 1. Let's say for example b is here and 1 is here. And we also know we have an asymptote as x equal to 0 for log function. So we can graph the asymptote at x equal to 0 and graph the function. It's something like this. Gets close to the asymptote but doesn't pass. So the domain of this function will be 0 to infinity, because I move left to right and start from 0, and the range will be negative infinity to infinity. Notice that we said before that exponential and log functions are inverse of each other. And if you remember from inverse functions unit, we said if you want to find inverse of a function, we switch the value of x and y. So here for the base points that we talked about, I have 0 and 1 for exponential, but for log I have 1 and 0. For exponential I have 1 and base, but for log I have base and 1. So that's also another way to remember how to make these two important points. Now let's talk a little bit about transformations. Transformation rules are exactly the same thing that we have learned before. So we're just going to review a little bit on this. If you have y equal to c times a to the power of x plus b plus a, or c times log of x plus b plus a, what does each of these values a, b, and c do to the function? Let's say the parent function is y equal to a to the x. So any kind of exponential function that you see, if you want to find the parent function, you just take the base and an x on top of it as the exponent. So that will be the parent function. And for any kind of log function, the parent function will be log of x with the base that you see here. So this will be the parent function. So what does a do to the parent function? Because this a is happening to the y value or outside the function, that moves the function up or down. So it's shift up or down. For example, y equal to a to the x plus 3. Or let's just put an actual value for a. Let's say 2 to the x plus 3. So this moves the 2 to the x 3 up. Or y equal to log of x minus 5. This 5 moves the log function 5 to the bottom. What does the value of b do? B is happening on the x value, so it's a horizontal transformation. So this is a shift to left or right. For example, y equal to 2 to the power of x plus 3. So this one, because it's plus 3, it's moving to the left, because inside, the changes to the inside is always kind of inverse. Instead of, although I have plus, but instead of moving to right, it's moving to the left. And y equal to log of x minus 5, this is moving to the right. Notice the difference between these transformations. The 2x plus 3, here the 3 is happening outside of the function, so it's moving up or down, but this 3 is happening on the x, on the exponent in parentheses, so this is moved to left or right. And also here, log of x minus 5, this 5 is moving up and down because it's outside, but this 5 is in parentheses, is happening to the argument of log, so it moves to the right. What does the value of c do? C, because it's happening outside of the function, it's a vertical stretch or compression. And that depends on the value of c. If the value of c is something between 0 and 1, then it's a compression. For example, y equal to 1 over 4, 2 to the power of x. But if the c value is greater than 1, then we have a stretch. For example, y equal to 4 times log of x. So this is the stretch. What happens if the value of c is negative? If you have a negative number before your function, this is reflection over x-axis. Now let's try to graph this function. When we're trying to graph a function like this, the first thing is to identify the parent function. The parent function, as we talked before, will be y equal to, we take the base and 1x on the exponent, because this is exponential function. So make sure you keep the same base and just write an x as the exponent. So this is the parent function. And we learned that the 2 points of this function is 0 and 1, and 1 and the base, which is 2 here. We also know that y equal to 0 is the asymptote of this function. So the first thing that I'm going to do here is to graph the parent function using this information, and then we'll talk about the transformation and graph this given function. So 0 and 1 is 1 point, 1 and 2 will be here, is my other point. And also we know that we have an asymptote here. So the graph of the parent function will be like this. I draw it with dotted point to say that this is my parent function, not the one that I'm supposed to graph here. Now, What transformations do I see here? I see left 3 because of x minus 3, and also up 1. So anything on this function will be moved left 3 and up 1. So I'm going to move this point left 3, 1, 2, 3, and then up 1. So it's here. And this point also will be moved 1, 2, 3, and up 1 here. Then I need to move my asymptote. Asymptote is a long horizontal line. So if I move it left or right, I won't see any change. But if I move it up, I will see the change. So this asymptote will be moved up 1, like this. Y equal to 1 is my new asymptote. And now this is my new graph. So this is the graph of y equal to 2 to the power of x minus 3 plus 1. Now what is the domain of this function? As I move from left to the right, I see that everything is covered because this function is continuing from left and right side forever. So it's from negative infinity to infinity. And the range, as I move from bottom to top, I see that this time is starting from 1. So it starts from 1 and goes to infinity. Okay, now let's graph this function. This is negative e to the power of x plus 2. So in this function, again, in order to graph it, we need to consider the parent function first, which is e to the power of x. And the two important points of this parent function will be 0 and 1 and 1 and 0. Then the asymptote of all exponential functions is y equal to 0. So this is my asymptote, y equal to 0. The 2 points are 0 and 1, and 1 and e. We know that e is equal to 2.7, so it's going to be almost here. So 1 and e will be at this point. So this will be the parent function. Now what transformations do I see? I have a x plus 2, that means left 2. And also I have a negative, that means we have a rock sum. So any point of this function will be moved 2 to the left and then reflected over x-axis. So move these 2 to the left and reflect over x-axis will be the other side of x here. And this point also 2 to the left and reflected over x-axis almost here. So if this is 1, 2, and 3, 2.7, negative 2.7 will be here. So it's going to be almost here. Then the asymptote, if I move it 2 to the left, I won't see any change. Even if I reflect it over x-axis, again, nothing will be changed because it's already on the x-axis. So this is my new asymptote as well. So y equal to 0 is the asymptote in both cases. Now I can graph my function. Just pass through these 2 points and get close to your asymptote. Now what is my domain? From left to the right, it's negative infinity to infinity, because this function is continuing forever. From this side is always continuing. And the range starts from negative infinity and stops at 0. So negative infinity to 0. Now let's graph this function. This is natural log of x minus 2. So the parent function is y equal to natural log of x. The two important points are 1 and 0 and base and 1. What is my base here? When we have natural log, base is always e. So these are my two important points, and the asymptote is x equal to 0. So if you find these information about your parent function, then it will be easier for you to graph the transformed function. So 1 and 0 is here, and e and 1 will be, if this is 3, e will be a little bit before that, it's here. This is e, and 1 is here, so it's going to be this point. And then we have the asymptote at x equal to 0, so it will be like this. This is the graph of uh, y equal to ln of x. So this is the parent function, not the original function yet. Now, what transformations do I see here? This is down 2. So everything that I see here has to be moved down 2. So the 2 points will move here and then like this. The asymptote is x equal to 0. If I move it down 2, I won't see any change. So it will remain the same thing. So this will be the graph of y equal to ln of x minus 2. The domain is still the same, 0 to infinity, and range will be negative infinity to infinity. Although I have moved this down 2, but still I know that this function is going to continue forever. So it's from negative infinity to infinity. The last function that we want to graph is this one. Again, first of all, let's find the parent function. Parent function is y equal to log of x minus 1, log of x base 2. This is the parent function. The two important points will be 1 and 0, and base and 1. Base is 2, 2 and 1. And the asymptote is always x equal to 0. So I start with 1 and 0, and then 2 and 1, and the asymptote is here. So the graph of the parent function will look like this. Now, what transformations do we see here? X minus 1 means right 1, and plus 5 means up 5. So any point here will be moved up 5 and right 1. So 1, 2, 3, 4, 5 and right 1. This one 1, 2, 3, 4, 5 and right 1. So these are the 2 points, and the asymptote, if I move it up 5, I won't see any change because it's a vertical line. And if I move it right 1, I will see the change, so it will be moved right 1. X is equal to 1 is my new asymptote. Now the graph will look like this. So the domain of this function from left to right, it's starting from 1 to infinity because it's continuing to this side. And the range, because this line is continuing to go to the bottom, starts from negative infinity and goes to infinity. This will be the range of this function. So this was today's lesson. I hope it was helpful for you. Have a great day.